Hi. Are you in motion? Are you moving right now? You might be sitting at a table. You might be sitting in a room, but are you moving? Well, if you think carefully about it, you're moving. If you're on Earth, anywhere, even if you're sitting somewhere, you're in motion. This is an important idea in physics. We refer to this as relative motion. You might have no motion relative to Earth, but Earth is moving relative to the sun. So it's an interesting concept to contemplate that we need to have a frame of reference in order to determine the motion of an object. This video is going to go over some of the details about that, how we analyze relative motion of objects or things. The objective here is to be able to use vector properties, addition and subtraction, to be able to solve problems where relative motion is involved. One of the key things here is frame of reference. So if you're looking at yourself and you're saying, hey, my velocity is 0, well, the reason you're saying that is because you're comparing yourselves to your surroundings. I'm not moving in this room, and that room is serving as a frame of reference. And in physics terms, we say that my velocity is 0 relative to the room because I'm not moving through the room. I moved no meters using the room as a reference. But in reality, I moved a whole bunch of meters just now because the whole Earth is spinning through space. So the value I get for my velocity or my acceleration, the Earth is accelerating. The position of the Earth is changing. Basically, all the quantities that we might be interested in depend on the frame of reference that I choose. And the answer could be anything. Depends on what frame of reference I want to use. You might say, oh, well, if I find my velocity relative to the sun, that's my true velocity. But the sun is moving. So it's an interesting question to ask yourself, what isn't moving in the universe? And you get a conundrum. The conundrum is, well, how would you know something is not moving? You would need something to compare it to that you know is not moving, which that doesn't make sense. So in physics, we don't worry about it. You just need something to compare to, and typically we use the Earth. So our most common frame of reference is the Earth. Now here's a fun question. Have you been to the Atlanta airport or a similar airport where there's a moving sidewalk? So in Atlanta, they have these sidewalks that go under the tarmac and take you from one terminal to another. It's fun to get on the moving sidewalk. So here I have an animation that I created to help you think about that. And it's an interesting sensation. It's fun. Here goes my guy. Whee! Why is it fun? Well, I have my theory about that. My theory is that it's fun because in a way you have two velocities at the same time when you're on the sidewalk. And I think it's a simple example to help you understand this equation that we're looking at here. So what we can say is that the velocity of any three things or substances or whatever it might be, and this is actually kind of interesting, this applies to pretty much any three things you want to name. The velocity of A relative to object B is equal to the velocity of A relative to object B plus the velocity of B relative to C. Did I say that right? A relative to C is a combination of A relative to B plus B relative to C. So the second letter in that subscript is whatever we're comparing to, and typically would, more specifically be a frame, what we call a frame of reference. The same equation might be written this way without the slashes, so it's a little bit more compact, so you might see it both ways, but it means the same thing. The second letter would be what we're using as a frame of reference. Let's go back to our moving sidewalk example. So here I've got pretty much the same animation, but I added the letter S to the sidewalk to make it easier to follow. And here goes my guy. And if you think carefully about what's happening, if you move on the sidewalk a certain number of meters, and at the same time the sidewalk moves a couple of meters, then you'll move that combination of meters relative to Earth. So that applies to your velocity. The velocity of the person relative to the Earth is the velocity of the person relative to the sidewalk. That's how you're walking on the sidewalk, plus the velocity of the sidewalk over the Earth. Well, even if you were standing still, the sidewalk would move you. So it's a pretty simple idea. You get on the sidewalk and your velocity gets added to the velocity of the sidewalk. And that's we see the result in the animation is, okay, well, I'm going faster now. Let's watch it one more time here, thinking about that. So you're walking along. Now you're still walking along, and then that's that weird sensation. So I think that's what makes it fun, is it seems like you have two velocities at the same time. If you think about what your feet are doing, you're thinking, oh, I'm just walking. But when you look at your surroundings, you can tell you're moving fast, in spite of the fact it doesn't seem like you should be moving fast. So those two velocities, your brain is kind of receiving mixed signals from your various senses. It seems like you have two velocities at once. And you know what? In physics terms, you do. Your velocity is either one of those. It depends on what we're interested in. Your velocity is one thing relative to the Earth, and it's something else relative to the sidewalk. I have a different animation. Let's look at this. And this is seen from the perspective of the sidewalk. So this is kind of freaky. Watch carefully, and you might want to rewind the video and watch this. So here, the sidewalk is at rest, and everything else is moving. And that's a perfectly valid frame of reference in physics terms. We don't have to use the Earth as a frame of reference if we don't want to. So that's an interesting perspective. Here it is one more time. Sidewalk sitting there, everything else in motion. Choice of reference frame is an interesting concept. What does it look like? Now, it is a vector thing. So you might be guilty of doing this. Have you ever done this on a moving sidewalk? Move backwards, yeah. Turn around, go backwards. That is interesting. So what is your direction on the sidewalk? That impacts your velocity relative to the Earth, and that makes this a vector thing. It's not just your speeds combining, it's your velocities combining. If you turn around and go backwards, you have a negative, so to speak, velocity relative to the sidewalk. And if that's great enough, you can overcome the positive velocity of the sidewalk, so to speak. So it's a vector phenomenon that we need to understand. Here, I have an animation that illustrates something that pilots need to be familiar with. So check this out, watch this animation. We're viewing an airplane from above, and here we can see some clouds, and below that we see a couple of buildings and maybe some roads, an intersection of a roadway. But watch what happens if I set this into motion. We see the plane is pointed north, but it's being carried by the wind. And that's an interesting situation for pilots. And they definitely need to be aware of this, that, hey, I'm pointing the airplane north, but I'm not going north. Well, actually, you are going north. It depends on your frame of reference. Relative to Earth, let's watch it one more time, and I've added this red arrow here. The plane is following this path diagonally across the Earth. And in words that pilots use, the plane has a certain ground speed. It will cover a certain amount of ground over the Earth. And it's on course. Hopefully it's on course. It's heading for some destination, and the actual path followed over the Earth would be the course of the airplane. And those are words that would be describing the velocity relative to Earth. But there's also this perspective. So watch this. This is kind of freaky. What we're going to do now is we're going to float along with the clouds. Imagine we're in a hot air balloon, say, floating and being carried by the wind. And now we're watching this airplane as we go along with the clouds. Notice the plane is ending up in the same place. We're not changing at all what the plane is doing. We're just changing our perspective. In this perspective, if we could use the clouds as a frame of reference, in essence, we're using air as a frame of reference, then this is the motion of the airplane in that frame of reference, and it is north. In pilot speak, that would be the airspeed of the plane. You go through a certain amount of air, a certain number of miles of air per hour, and that would be the airspeed of the plane. And the plane is pointed in a certain direction, and that's actually an important word, heading. It's a very literal word. It's the way the plane is headed, pointed. And that's an interesting thing for a pilot to cope with. You might need to point in a direction different than you're actually trying to go, right? I'm trying to get from point A to point B on the Earth. Here's another perspective. Here we have a reference frame, which is the plane. What if we use the plane as our frame of reference? Everything else is moving. And in this perspective, we can say, all right, well, the air is moving relative to the plane, the Earth is moving relative to the plane, and those velocities would be equal and opposite to the previously described velocities. So the velocity of the Earth relative to the plane is opposite the velocity of the plane relative to the Earth, and likewise, plane relative to air, air relative to plane. Now, if we want to apply our little formula to this situation, it would look like this. And notice the formula, the letters are in the same order. They're always in the same order. So if we have this, this phenomena, relative motion, we can always trust that formula if we write the letters in that order. A relative to B, A relative to C, A relative to B, B relative to C. Well, here it's P relative to E, P relative to A relative to E. So always in that order, and in this case, that would be the ground speed is the resultant. Ground speed and course would be the resultant, adding the motion through the air plus the motion of the air. It's actually very similar to a moving sidewalk. The airplane is on a moving sidewalk in the sky, you might say. So as the air is moving, the plane is being carried by the air. And in this situation, I would have to form a triangle to analyze the motion. So I hope this makes sense to you looking at that figure. It's a head-to-tail diagram illustrating what the formula says. So this formula is kind of a curious formula. In some ways, we typically aren't plugging numbers into it so much as using it as a way to understand what to do with some vectors. Put them head to tail, and then I find this resultant. Here's the same thing from the frame of reference of the air. It doesn't change the relationship here. Like, it's the same triangle. Whatever frame of reference I'm using, I should have the same figure if I think about how things are related to one another. Here's a different example of relative motion, being in a river current. So here we're imagining some people in a canoe. One of the most mysterious things about this is, why is this guy wearing a suit and tie? Well, I don't know. Maybe they're on their way to a wedding in a canoe. So that was one frame of reference. That's what it looked like. But now a different frame of reference. What if we float with the water and we are floating downstream and we're watching them move in the relative frame of the water? This water might be moving, say, 4 meters per second west. But the boat might be moving through the water 3 meters per second east. Well, what happens if you put those things together? We could write our formula very similar to what happened with the plane, but now it's the boat relative to the earth is the combination of the boat through the water plus the water relative to the earth. I added some reference frames here. So actually a reference frame needs a coordinate system. So X and Y coordinates. More broadly, what is a reference frame? Typically you would have some sort of established coordinate system. So here is the motion that we were just watching. And if you think about it, the numbers in the problem. So the water relative to the earth was 4. The boat relative to the water was 3. So the combined result here, head to tail, I'm going to end up with like a -1. So our people, if they're headed for a wedding, they might be late because they're not making progress. They're actually not moving fast enough to go upstream. They're actually getting carried downstream because they're moving slower than the river, moving through the river slower than the river is moving relative to the banks. So given those numbers, we could conclude, their velocity relative to Earth would be 1 meters per second west. That would be relative to the shore, and if they're in the boat, they would see the shore drifting by at 1 meter per second, or if you were on the shore looking at them, you would see them drifting by at 1 meter per second. Same motion from the perspective of the water. So we imagine painting this reference frame on the water. We move with the water, and it looks different, but it would be the same result. Here is one last illustration with the water in the canoe. Maybe they're trying to get across the river. So if they want to cross the river, say from one dock to the other, how do they do that? Well, if they don't adjust for the current, they're not going to go straight across. And that's actually kind of an interesting one to think about. So relative to the water, it looks like this. They're actually moving diagonally through the water. But to get straight across, we have this combined effect. And this is just like the previous animations, but now it's not linear motion, it's this two-dimensional motion. And if the water is still going 4 meters per second, let's suppose they want to go north 3 meters per second, well, then they're going to have to move through the water at 5 meters per second. And they're going to have to move in a certain direction through the water, headed in a certain direction to get to their destination. Same triangle in either frame of reference. The last thing in this discussion of frame of reference is this question. Let's suppose you're in a car. Suppose you're in car B, and car A runs into you. Car A is traveling at 40 miles per hour, and you're going 30 miles per hour. How bad is that collision? Well, it depends on what's happening, actually. The answer could be any of the values shown, A, B, C, D, or E. If this were multiple choice, you don't have enough information to decide. This would also be a frame of reference problem, and this one might seem a little more abstract. The airplane in the air is more concrete. The boat in the water is kind of concrete. The person on the sidewalk is sort of concrete. But this is a little bit more abstract because we're just talking about how one thing moves relative to another. Let's just look at these. I've got several things animated here. So let's suppose that the cars are going in the same direction. You're in car B, and there comes car A. Oh man, car A ran into me. Well, if we wanted to, we can view this from your frame of reference. And that's what it's going to be like. It's a collision where, in your perspective, the car A is hitting you at a certain number of miles per hour, and it's not 40. It would be gaining on you at 10 miles per hour, which is the difference, and that's consistent with the formula. A relative to C equals A relative to B plus B relative to C. If you solve for A relative to B, you would subtract, and that would give you 10. And notice that also satisfies head to tail the original formula, A relative to B, which is the purple arrow, plus B relative to C, which is the red arrow, is equal to A relative to C, which is the blue arrow. C in this case was basically the earth or the roadway. So one possibility, if you're moving in the same direction as the other car, is that the impact is like a 10-mile-per-hour crash. And it satisfies either way you want to look at this. It's the same concept. Are we subtracting the vectors? Yes. If we started with 40 and 30, we would need to subtract the vectors to get this answer 10. But that's consistent with the end result, like these vectors show the vector addition property that we would expect. What if this happens? Now this, of course, would be a lot worse. If you're in car B, and then here comes car A head on, this would be a very dangerous crash. Let's hope this never happens to you. But in this situation, if you're in car B, it looks like car A is going 70 miles per hour, and the crash is that bad. It might as well be going 70 and you being at rest. What is moving and what isn't? There's not an answer to that question. In physics terms, all that matters is one thing relative to another. What are we interested in? In this case, we're interested in, well, how bad is this collision? How bad is A moving relative to B, or how fast is A moving relative to B? Here again, we would be subtracting vectors, but B relative to C, if I'm subtracting it, well, it's like a negative compared to A relative to C. And then that would give us this answer, 40 minus negative 30, which makes perfect sense. It also, once again, would satisfy our original relative motion equation. Like the three vectors shown are head to tail. The purple plus the red is equal to the blue head to tail. Here's one more possibility. Suppose you have a collision at an intersection, and C is the intersection. So in one frame of reference, it looks like this. Oh man, I just wrecked. Who ran the stoplight? I don't know. But if we see this from your perspective, what does it look like? This one is interesting. So now if you're in car B, it looks like this. Yikes. Here comes A at me, and also this A seems to be moving east and south, and that's a result actually of me moving north in a way. But we could find the velocity in that frame of reference, and that would be a vector operation. I need to use the Pythagorean theorem to get 50 miles per hour, which would represent this arrow. And that's what we saw car A do in the frame of reference of car B. And that once again would satisfy our original equation. So this is actually fairly important to be able to find the velocity of one object relative to another for certain problems. I hope this lesson has been interesting and helps you understand relative motion and frames of reference.